Alright, my little faculty meeting is over, so let's continue on with part two. Gonna get into some a little more interesting, challenging problems, a little bit of actual calculus involving vectors. So let's start off with this amazing little problem. A Boeing 727 airplane flying due east at 500 miles per hour in still air, which means that's the speed in still air, encounters a 70 mile per hour tailwind acting in the direction 60 degrees north of east. The airplane holds its compass heading due east, but because of the wind acquires a new ground speed and direction. What are they? Okay, so basically, if it wasn't for the wind, the airplane would be flying exactly east, like 100% straight east, but the wind sort of pushes it off course, and it also changes the speed. Okay, so we can use vectors to sort of do that. So over here in the pic, again, like throwing all of the final product of the picture to you at once might be a little overwhelming or whatever, but so this is the 500 miles per hour, and again, like the length is the speed, the velocity. Okay, again, I don't want to convolute the words speed and velocity. I know, especially from physics, I think those two words mean like not a very different thing, but they're technically different. But so 500 is the magnitude, the velocity, and so that vector arrow is going directly east. And then the wind is blue. So the wind is going 70 miles per hour. So the magnitude, I almost feel like I want to put that there so I can talk about the angle. But so that's 70 miles per hour, and the angle, okay, is 60 degrees north of east. So just gotta learn how to wrap your brain around that lingo, I guess. And so you can pretty much attach the wind vector here to the end, and you have like this overall purple vector when you add them up. So we're literally going to add the two vectors. Okay, now actually it's probably down here first, right? The u vector and the v vector. So I might have been getting a little ahead of myself here. Now the u vector is what? Like 500, 0. And then the v vector is, well, what is the v vector? How do we find the v vector? We need the, like the a value and the b value, Like we need the components. Like we know that it's 70, long, and we know the angle, but, so this is where we got to call upon, again, our pre-calculus skills. And if you think about it long enough, right, this is how we're going to figure out, so it ends up being like 70 times the cosine of 60 to get just the a component, and then the b component would be 70 times the sine of 60. And so it looks like we're able to kind of do this exact, but approximating, obviously approximating what 35 root 3 is, or basically approximating what 70 times the sine of 60 degrees is. I mean, I'm sure it'd be okay to go ahead and just approximate that answer. But now we can get to here. And so the purple vector, you know what I mean, that represents what the plane is actually going to be doing. You just add these two vectors together. And so 500 plus 35, ba-bam. And then 0 plus this, is that. And again, I'm probably moving these boxes a little too soon, but so that's the purple vector. But the final answer is not just what is the standard representation of the plane's like final vector. They want to know the new ground speed and the direction. Like what's the new velocity or speed? What's the new direction? So we have to find the actual magnitude of this new vector, okay? And that just involves the Pythagorean theorem. So nothing too crazy there. And then the angle, how are we going to find the angle of this purple vector? Just knowing, well, I guess now we know the length of that. But what if we just kind of went with knowing the A component and the B component? Could we use trigonometry to figure out? I mean, you betcha. Long story short, inverse tangent of B over A. I'll say that again in case you want to literally write that down. That, just to remember, to do this properly, it'd be the inverse tangent of B over A. Alright, and then your calculator can take care of the rest of that, and I don't think there's any big surprises. I mean, if you remember, technically you get, like technically there's infinitely many answers, right? But somehow you have to kind of, and I'm betting your calculator is going to tell you this particular answer of 6.5-ish degrees. Anyway, so those are those answers. Let's move on. So are we now getting into a little bit of calculus here, maybe? Let's see. Recall if we have s of t, which is position, taking the derivative will give us v of t. Yeah, I remember that. And taking the derivative again will give us a of t, acceleration. It works the same way with an object moving in the plane, because we can model position, velocity, and acceleration with vectors and treat the components of the vectors as separate linear models. Okay, I think this should overall be a pretty quick, clear example. But a particle moves in the plane, so that's position at any time, t greater than or equal to 0, is given by this. So this is not necessarily a vector, it's just kind of like this is the position, like coordinates or whatever, you know what I mean? So this is the position, okay? It's based on the sine of t comma t squared over 2. So the position vector, alright, you could just say is actually the same thing. Because if that's literally the coordinates, find the position vector. Let me just make sure I can wrap my brain around this. The coordinates at any time, so the position vector. I mean, yeah, especially, I don't know if this is like a big detail, but exactly at 0, we're positioned at 0, 0. But anyway, maybe I'm overthinking that. But so here's the position vector, and then the velocity vector. You just take the derivative. Okay, literally, like you've been doing since you had Mrs. Klut's class, early on in Mrs. Klut's class. So velocity is the derivative, so just the separate components. Easy. Same with acceleration. Just kind of take it, one more step, and you take the derivative again. So yeah, easy. Very simple. Now describe the position and motion of the particle at time t equals 6. So I think here we're just going to kind of plug in 6 to all of these different vectors. And like that's how we're going to describe, like when it says describe the position and the motion, it might as well be saying describe the position, the velocity, and the acceleration. So all we're doing is literally plugging in 6 for t, I believe. So the position is going to be, roughly this, and I guess I'm kind of approximating, the sine of 6. Okay. I'm going to assume that this is radians. Double check on that. Okay, but I'm going to go off the assumption that we're doing the sine of 6 in radians. And then let me know if that's not, correct. And then when we plug in 6 to the velocity, and hey, taking it one step further, not just finding the velocity vector, but going ahead and finding the magnitude, and the same with the acceleration. That actually makes sense now that I think about it. That to properly describe the motion, that we would find the magnitude, the Pythagorean theorem gimmick of this velocity. So like the velocity is 6.076. And describing the angle of the movement. You know what I'm saying? So wow, really thorough here. Not only the actual velocity, but the direction, the angle of direction, or whatever. And then the acceleration, just plugging in 6 for t, and finding that magnitude with the Pythagorean theorem. And yeah, so okay, all right. So far, so good. Velocity, speed, acceleration, and ooh, you might want to put a star on this one or something. Direction of motion. This is like almost its own like vocabulary term or something. But the direction of motion. So if, let's see, so just kind of a given, suppose a particle moves along a smooth curve. So its position at any time is, okay, where x and y are differentiable functions of t. So the position vector, okay, r of t, okay, so r of t is the position vector. That's cute. But so that's the position vector. All right, that's the position vector. And then of course the velocity vector is just going to be the derivative of that, or like, I was thinking x prime of t, but same thing. The particle's speed, right, is the magnitude. And when you're doing this magnitude thing with the Pythagorean theorem, it's always going to be positive. And so I'm thinking really quick, that's why we can use the word speed. I think that has something to do with it, right, in physics, where speed is always positive. I could be wrong about that, I'm not going to call up Mr. McIntyre right now or anything, but so speed is a scalar, not a vector. It's just a number. Like you don't describe speed as a vector with components. Okay, because there we go. Like I think right there we just sort of tripped over like a pretty good distinction, right? Velocity, the velocity included in that term. Velocity is not just about how fast you're going. Velocity also is about your direction. So velocity makes a lot of sense to use a vector, like with two different components, because the direction also matters with velocity. But speed's just a scalar. Speed's always positive. Speed is not really taking into consideration your direction. It's just your speed, okay? So speed's a scalar, not a vector. I think that should make sense. And then the acceleration would be obviously the second derivative, x double prime, comma, y double prime. Now, the direction of motion, again, like you should make special note of this. This is like a very special term or thing, is the direction vector. But the quote-unquote direction of motion, okay, you calculate by doing the vector, the actual velocity vector, divided by the magnitude of that vector. All right, so you essentially so to get the direction of motion, you basically multiply the velocity vector by 1 over the magnitude of the velocity vector, or the speed, you know. So you divide the velocity vector by the speed, essentially. So remember, you can think of this as a special teeny little formula, okay, like a little mini formula. That's very, very, very important when they specifically ask for the direction of motion. Oh, this might be the juiciest example in the whole lesson. Baseball. Ugh, not a very big baseball fan. Sorry, that was beside the point. I like baseball enough, whatever. A baseball leaves a batter's bat at an angle of 60 degrees from the horizontal. So I already have this little picture cooking down here. So the horizontal of the batter's bat, and then 60 degrees from the horizontal. Traveling at 110 feet per second. All right, so the magnitude of this vector, you know, I guess at least at first, is like 110 feet per second. 110. A fielder who is standing in the direct line of the hit with his glove at a vertical reach of 8 feet. So the glove is 8 feet above the ground. Catches the ball for an out. His feet do not leave the ground. Find the position vector. Find the position vector of the baseball at time t in seconds. Find the position vector. So what we know is that this angle, you might want to write this down. I don't know why I don't actually have. Whoa. What font is that? What the heck did I just do? I like me some Comic Sans, though. So there's like little... Oh, man, what the heck? The angle is 60 degrees, isn't it? So we know that that's the angle, and we know that like the length of this is 110. Okay? So you can write that down in your notes. So knowing those two values, we're supposed to find just like the position vector, okay? The position vector. And what makes this extra juicy, note that this ignores height of the ball when hit. So we're not actually considering how high, I mean, it seems that way. We're not considering how high off the, like we're considering that the glove is going to be 8 feet off the ground, but we're not actually considering how high off the ground the bat is, or how high the ball was off the ground when it was struck. We're not considering wind, even though that would be a factor. Just ask the airplane. And we're not considering air resistance. Jeez. We only are going to consider gravity. So please please notice this, okay? We are actually going to consider gravity. This is getting real heavy real quick. Physics. So long story short, here we go. The horizontal component, the x component, considering little trigonometry here, 110 t times the cosine of 60. All right. 110, is the feet per second. So every second, basically, it goes 110 feet. So if t, don't get confused by the fact that there's a t here. So like at t equals 1, so I guess I can put this 110 right here after 1 second. So after 1 second, the arrow is a certain length, but after 2 seconds, it's, going to be longer, right? It's going to be 220, you know what I'm saying? So I guess, I didn't really consider that right away. I didn't really notice what I was doing, in live time. The length of this arrow is not necessarily 110. 110 is the velocity, it's the speed, right? Technically, 110 is the speed, okay, not so much the velocity. And so it's not like this arrow is 110 feet long. It's only 110 feet long after 1 second. So I guess you would technically, wait, what? Why does that make? I don't know why that was. Maybe my caps lock was on or something. So technically, the length of the arrow, I hope this makes sense, is 110 t. I told you this problem was juicy. Now, the vertical component is affected by gravity. So therefore, we're going to throw on this minus 16t squared. Now, if you've taken physics already, and you've seen this in physics, like maybe this will make sense. But long story short, this minus 16t squared is because of the effects of gravity on this baseball. And so this is and then I guess we could clean this up. Yeah, we clean this up a little bit. What is the cosine of 60 times 110, blah, 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 blah. So this is the position vector, and that's part A. That's all part A wanted, the position vector. Find the velocity vector. Okay, well, that's not too big of a leap. So how do we go from the position vector to the velocity vector? We just take the derivative. Okay, that's not so bad. So we took the derivative, and this is what we get, right? So there's the velocity vector. So far what we've been able to kind of dissect from here. I know it was a little bit of a rough patch for a second there, and a little bit that was my fault. But as of right now, we have the position vector of this baseball at any given time, and we have the velocity vector, what the actual velocity is, as well as the direction, based on what the time in seconds. All right, so that's what we have at this point. Part C. At what time t does the fielder catch the ball, and how far is he from home plate? So how are we going to figure that out? How are we going to figure out when the ball is caught, by this fielder, this outfielder or whatever, that has a vertical reach of 8 feet. So he's going to catch it when the ball is 8 feet above the ground. So when the ball's vertical component of position is 8, right? So I'm thinking we're going to take the y component of the position vector and find out when this would ever be equal to 8, right? Wouldn't that get the job done? Is that what this is. Yes. Yes. All right. Now, holy crap. I think what's going to happen here. So now we have to solve this. So we set it equal to 0. Okay, now long story short, I don't want to blow this out of proportion, okay? Math pun, proportion, get it. But it looks like here, I mean, look at this nasty square root of 3. So I think what's behind these boxes are going to be the quadratic formula. But if you want to throw this into Desmos, remember, you can cheat that way. Like, you can throw this into Desmos with it being like equal to y and look for the x-intercepts. So you can almost like skip this part, all this, yeah, I told you, all this nasty number crunching with the quadratic formula. You could just throw this into Desmos or your graphing, or heck, your graphing calculator, right? And you could like see where the x-intercepts are. Long story short, again, I don't want to like make too big of a deal out of like actually solving this equation. The overall concept here that I'm trying to get across to you is we like where this equation even came from so that we can answer this particular question. So solving this equation is not a new thing. You know what I mean? Like you know about the quadratic formula. You know about throwing it into like a graphing calculator or Desmos.com to just look for x-intercepts. The bottom line is this was the equation, where it came from, and here is the two answers. I would imagine, like, you know, it explodes off the bat, and it's 8, you know, like almost like right away it reaches 8 feet, you know, like 0.085 seconds. But then after another, you know, but really it comes back down again and is caught, right? Like, I don't think the fielder was standing directly in front of the batter. Wow, that would be impressive, wouldn't it? Holy moly. To like jump right in front of the batter at the last split second and like catch the ball immediately coming off the bat. Oh my gosh, that'd be crazy. But no, it's not that. It's this. And how far is he from home plate? So wouldn't that be the x component of the position vector? So I suppose we could, no, not how far. So we could, like, for a second I thought we could like set this equal to 8, but no. No. That's not what we're going to do. The position vector, the component of the, you know, the x component is 55t. Now we know the t value. Now we know the t value, and we can figure out the horizontal component there of the position vector. And I'm trying to stick to the same color codes here, right? Well, for the most part, but it's like, well, I'm trying to stick to like the position vector. You know, I think I'm going to try to stick to whole, like, just so you know, so it helps, you know, keep you from being confused. I'm going to. I think in this presentation I stick with like this pink color for position vector, this bison blue color for velocity vectors, and this crappy green for acceleration. But so here we go, using the, I don't know, shade, darker shade, but the red here, and we're just going to plug in that t value and get 322.795 feet. So I know these problems are a little weird and crazy to you now, but I think these steps will make sense to you. All right, how fast is the ball traveling when he catches the ball? So how fast is it going? So that's not exactly like, it's not just velocity, it's like the speed. So we're going to use that t value that we already have now, and I think we're going to, oh my god, did I just like break my own, what I just said? Let me fix that. There we go. So plugging in that t value, so this would be the velocity vector, you know, at that time. So here's the velocity vector, but this also includes like the direction that it's going at that particular split second. They just want how fast, which is the speed. So this is what we got to do. We got to take the absolute value, the magnitude of the velocity vector that we get here, and that's just going to involve the good old Pythagorean theorem. And this will get us the feet per second, which I suppose if you cared about miles per hour, I don't know why we would. The original units it's talking about is feet per second, right? So whatever. I mean, maybe this should just give you an idea, like, because you're, people driving cars. I guess you have more of an idea of what miles per hour is all about. But 107.655 feet per second. Gosh. So yeah, velocity is blue, people. Yeah. Ooh, new example. Okay, new example. A particle moves in the plane. You know how particles do that. Particle moves in the plane as they do with this position vector. Ooh, fancy. So this would be the position vector at any time t of this particle. Find the velocity and acceleration vectors and determine the path of the particle. Well, as far as finding the velocity and acceleration vectors, I mean, it's easy. Just take the derivative and then take the derivative again. And the path of the particle, well, guess what? Determine the path of the particle. I mean, you can't really... I mean, if we wanted to determine the path of the particle, like at a particular second, we could find like the magnitude of the velocity or something, and the angle and stuff. But I mean, like the overall path of the particle, here's what we're going to do. We're just going to graph this in parametric mode. I think I've already addressed this in a previous video about how you can graph these things. But look, you can treat this, it must have been in the 5.1 was the parametric lesson, so probably in that video. But we can totally treat this as a parametric type deal, like a parametric type set of equations, and just graph this, okay? Oh man, that's good. Like how we can just kind of graph this on our graphing calculator in parametric mode, typing in this for the x part and for the y part, and then you can like sketch that graph or describe it or something. But yeah, that's it. That's all I really need, or that's what that means. Next example. Okay? A particle, moves in an elliptical path as one does, so that it's elliptical. That means oval. So that's position at any time t, as long as starting at 0, is given by this. All right, so that would also pretty much be the position vector. Man, okay, so again, it starts off real easy. Find the velocity and acceleration vectors. What's the derivative of 4 sine of t? Gee, George, that. What's the derivative of 2 cosine of t? Gee, George, negative 2 sine of t. And then taking the derivatives again to get our acceleration. Now, I assume, this is just part A, I assume we're going to be using these vectors to answer more complicated questions in part B and beyond here. Okay, so here we go. Here's our velocity vector, here's our acceleration vector. So we have those now. We have all those vectors. Okay. Find the velocity, acceleration, speed, and direction of motion. Ooh, direction of motion. That fancy, that guy. At this second, this time. Pi over 4. Now remember, people, velocity, you describe velocity literally as a vector, So finding the velocity, you're going to be finding a vector because, notice how they want speed. Speed is just going to be that like one number, but velocity is given as a vector so that it can describe not only like the speed of it, but also the direction, because the direction's included in velocity. So again, for velocity and acceleration, these first two parts are going to be super simple. All you're going to do is literally plug in that value for t. Use your calculator to help you, and boom bam, like there's the velocity vector. Okay? You must think I have the worst OCD of anyone you've ever met. You might not be wrong. And here's going to be the acceleration vector. Easy peasy. And so then the speed, remember, how do we find the speed? The speed would be the magnitude of this velocity vector. So yeah, the absolute value, same thing, magnitude. And so we just do the whole Pythagorean theorem gimmick, and we end up with the square root of 10, which I suppose you could approximate. You know, and then the direction of motion, remember, the direction of motion has a very specific definition. So this was the direction of motion, and so that's all we're going to do. And remember, this is a vector. Okay, and this was the speed. We just found out that this was root 10. And so ultimately, you know, you find the direction of motion by doing this. Please make sure you can understand and wrap your brain around how this is what we're ultimately doing to find the direction of motion, quote unquote. So now all we got to do is like distribute, for lack of a better word, you know, or like kind of multiply this scalar, this speed, or 1 over the speed, to both of these components, and you get that. Okay, so direction of motion is also a vector. Okay, easy. Sketch the path of the particle. All right, so the path, so you can just I'm actually not sure why I have that written down, so I'm going to cover that back up. So what do we got to do here? We got to sketch the path. You can just use your graphing calculator and plug in, you know, in parametric mode. Plug in those two mamma jammas, and you get the ellipse, like it said. It told you it was elliptical. And show the velocity vector at 4, 0. So show the velocity vector at 4, 0. So again, I don't think this is necessary. X equals 4. Yeah, x equals 4. So sine of t equals 1. I think all this, again, I think this was unnecessary, but what this shows you is that your time value, so at this position, at the position 4, 0, I think that shows like what time value you would be at, but I don't think we even care about that in this. So yeah, I think this was all unnecessary, but I think this shows that your time value would be what, like pi over 2, because the sine of t equals 1 at you know, the sine of pi over 2. So I think all that shows is like when you'd be at that position, but I don't think we even care about that right now. What we care about is the velocity vector. So all you got to do, people, is oh wait, maybe we did care. No, wait. Did we care? So I guess we could have just plugged in. Yeah, okay. Maybe we did care. Hmm. Okay. Yeah, I guess when I would have got to here, I would have thought like, okay, so what are we going to plug in for t? So then you just kind of. So I guess here we could. I mean, the point is like the cosine of t is going to be, well, flat out 0, or t itself, t specifically, could be pi over 2. And then again, the entire sine of t is 1, or you could just kind of, I think where my brain was going there was just, or just literally plugging in pi over 2 for t itself. Bottom line is, you end up with this velocity vector, and so you're going to like literally draw that vector, you know what I mean, at that point, you know what I'm saying? So I mean, this would be like the standard representation, but in actuality, like the vector, at that moment, so the particle is going like directly down, okay, based on this vector exactly at that moment. So like I said, this was like the pi over 2 time mark, that second. When t equals 0, right, at the t equals 0 mark, let's see, 4 times 0, so 0, 2, so it looks like at the very start we were at 0, comma 2. So the path of the particle like starts up here and goes like this, bam. And so at this exact moment it's heading directly down. And I think when your calculator draws it, I think it would like literally start, especially, and again, I don't know if you have to actually plug in like certain t values into your calculator. I can't remember if you have to do that or you can do that. But I think your calculator will literally draw it starting here and go like this in this direction. You know what I'm saying? But anyway, probably spent a little bit too long on that problem. Distance and displacement and distance. Displacement and distance traveled. Okay, remember people with velocity and stuff? Remember how Mrs. Clute taught you how connected with all that was like distance and displacement, or displacement and distance. So here we go. Some quick definitions that you need to make special note of. Essentially, they are formulas, okay? Pretty much formulas. So if you have a velocity sort of vector, okay, the displacement would essentially be this vector. So displacement is a vector, because isn't like displacement kind of like a position? You know what I mean? Displacement's kind of like a position, like your final position. So it makes sense that displacement would be an overall vector. But the distance traveled, is going to be an actual number. So, and remember how like to do all this, you would like integrate velocity back with Mrs. Clute. So pause the video if you need to finish writing all this down, but this is pretty much how you're going to do displacement and distance. Essentially formulas. Okay. Example. A particle moves in the plane, as particles do, with a velocity vector. Maybe we shouldn't be using parentheses. Who cares? Parentheses prevent from sneeze. The bottom line is, you have this x of t, or like v1 of t, I guess, actually. Like v1 of t and v2 of t. At t equals 0, the particle is at this point, this position. At t equals 0. This sounds like an initial value. Find the position of the particle at t equals 4. So we have velocity and we want position. How do you go from velocity to position? Well, we're talking about displacement, we take the integral. So integrating from 0 to 4, okay, from 0 to 4, this is what we get. All right. And so using our calculator to 17 minus 1. I mean, you can, or you just could have like used your calculator outright, but so 8 comma 16 is the position. Okay, or actually it's the, no, it's the displacement. Sorry. So let's make sure we get a grip on what we just found. So doing all this with the velocity, we just found the displacement. This is like the vector representation of how much we've been displaced, like our net displacement, considering that we started at 1 comma 5. So if we start, see, what we want here is the position. We don't want, so this is, okay, so this actually kind of threw me for a little bit of a loop at the beginning, Ultimately, we wanted the position. Okay, now to do that, we find the displacement, so we can kind of compare our displacement to where we started from. And so if that was our starting point, and then after 4 seconds we were ultimately displaced like that, then our final position must be at 9 comma 21. Makes sense now? It does to me. This was displacement. Part to B. What is the total distance traveled? Well, okay, so going back to our formulas or whatnot, this is all we do, people. So we follow the formula to the T, get it? And throw it into your calculator, and I don't know. I mean, this was really straightforward. They were literally asking for the total distance. Just like back here, if they were literally asking for the displacement, this would have been your answer based on this little, formula or so. But so pretty straightforward. Okay, we can do this. Determine the path that the particle travels going from 1 comma 5 to 9 comma 21. So determine the path. So now look, based on what we've been doing already in this lesson, determining the path is essentially just going to mean graph it. Graph it using technology, using your parametric mode, and then like describe it or sketch the graph, literally from your calculator. But guess what, people? In order to graph it, don't we need like the position vector? Like don't we need like the position functions? So because we have like the velocity, so we need the position, because we got to know what to plug into our calculator. So we're going to integrate, get a couple plus c values, right? And then I think this is why I had that. I think that's why I had this like initial reaction, because this was pretty much like an initial value when t equals 0, x literally equals 1, and y literally equals 5, as far as like a position vector, you know what I mean? So once we do this, right, and yeah, again, we have like a couple of plus c values. Now you can use the fact that all of these are true at the same time, plug them in, and solve for c. So blah blah blah, like busy work or whatever, and we end up with c equals 1 for this piece of business, this x component, and c equals 4 from this component. And so, people, here is essentially the two components of your position vector. So we had our velocity vector, basically. We literally integrated to get back to position, you know what I mean? And this you can treat as like a parametric type deal and plug that into your graphing calculator in parametric mode, and that's how you quote-unquote determine the path by asking your calculator. And that's it. So there was a couple little mini bumps along the way, but I mean, vectors and a lot of so the calculus part of all these vectors, like it pretty much all revolved around position, velocity, and acceleration, didn't it? Which you have a very strong foundation of, so that's good. But yeah, that's all I have to say about that, I guess.